Welcome back, everyone. Today we're exploring one of the most elegant and honestly most powerful tools ever conceived in the world of physics, the Mach-Zehnder interferometer. This explainer is going to take us on a pretty incredible journey. We'll trace how a single fundamental concept, literally just splitting light, has scaled all the way from visualizing macro-world physics right down to driving the micro-world of modern silicon photonics.
Okay, let's dive into this with a question to really frame our thinking. How can a single beam of light both see the invisible air around a fighter jet and, at the exact same time, serve as the microscopic engine powering the global internet? I mean, it sounds kind of like magic, right? But it's not. It's pure, beautiful engineering.
So here's our roadmap for today's explainer. First, the magic of splitting light. Then, seeing invisible airflow. Third, driving modern optical communications and MEMS. Fourth, exploring quantum entanglement and erasure. And finally, building future quantum computers.
All right, let's kick things off with Section 1, the magic of splitting light and the foundations of interferometry.
You know, this elegant manipulation of light is something that's built up over centuries. It's almost like a giant puzzle. It all starts way back in 1802, when Thomas Young proved that light actually behaves like a wave. Fast forward to 1891, and Ludwig Zehnder proposes a clever new way to split those waves. The very next year, Ludwig Mach, who, fun fact, was the son of the famous Ernst Mach, refines the design into what we now call the Mach-Zehnder interferometer. And today, that exact same foundational architecture is being pushed to the absolute cutting edge of linear optical quantum computation.
So how does this whole shebang actually work? Well, picture two hikers starting at the exact same point. You split a single, perfectly aligned beam of light into two. One hiker takes what we call the reference path, and the other takes the sample path. Because these paths are physically separated, you can put something, like a new medium or a gas, right in the middle of the sample path. If that hiker walks through a denser forest, they slow down, right? When the two light beams finally recombine at a second mirror, they arrive slightly out of sync. This out-of-sync arrival is called a phase shift, and measuring that shift gives us absolutely incredible data about whatever was in that sample path.
Now, what's really interesting here is the visual output. Based on source material, looking at a candle flame through this device, you get two very specific images. If the light waves recombine perfectly in sync, their peaks add together. That's constructive interference, creating a bright, visible white flame. But if they arrive exactly out of sync, the peak of one wave meets the trough of the other. They literally cancel each other out in destructive interference, creating a dark black flame. Keep this in mind, because this binary output, bright or dark, is a real game changer for modern computing and photonics, which we'll get to in a minute.
Moving right along to Section 2, seeing invisible airflow in macro-world physics.
Because the speed of light changes depending on the refractive index of whatever medium it passes through, this setup is absolutely perfect for observing invisible gases. Think about it. If you change the pressure, the density, or the temperature of a gas in the sample path, you change its refractive index. That slows down the light, shifts the phase, and completely alters the interference pattern we see at the very end.
And let me tell you, this was an absolute game changer for 20th century engineering applications. You put an airplane wing or a scale model of a car in a wind tunnel, shine one path of the interferometer through that airflow, and boom, suddenly the invisible becomes visible. Engineers could visually map out shock waves, measure heat transfer, and even diagnose complex plasma physics. It gave us the visual data we absolutely needed to optimize the aerodynamics of modern transportation.
All right, a big pivot now to Section 3, driving modern optical communications and MEMS, the micro-world of silicon photonics.
So the crucial point here is this incredible transition. This is where we connect the dots to today's tech, specifically silicon photonics. We essentially took the massive mirrors and beam splitters that used to sit on giant laboratory tables and shrank them all the way down onto microscopic silicon chips. We're now steering and manipulating light at a microscopic scale, which has opened up an entirely new era of optical engineering.
And this brilliant miniaturization? It's exactly what's powering your internet right now. Remember that white flame and black flame from earlier? Bright and dark? Well, on a silicon photonic chip, a microscopic Mach-Zehnder interferometer acts as an optical modulator. By rapidly applying just a tiny voltage to one arm, we shift the interference from constructive to destructive. Bright, dark, 1, 0. That rapid pulse is literally the digital data traveling through global fiber optic networks. And beyond telecom, these micro-interferometers serve as highly sensitive fiber optic sensors for extreme environments and even biosensors for medical imaging. The exact same physics used to test a fighter jet's aerodynamics is now streaming this explainer straight to your screen. No way, right?
Let's zoom in even further. Section 4. Exploring quantum entanglement and erasure in the quantum realm.
Because the Mach-Zehnder isolates light into two incredibly distinct paths, it's actually the perfect laboratory for observing some of the strangest, most counterintuitive phenomena in quantum mechanics. We are talking mind-bending boundary pushers here, folks. Multipartite entanglement, the famous quantum eraser experiment, the quantum Zeno effect, and even the Elitzur-Weidmann bomb test. That last one is a scenario so fundamentally weird that you can detect an object's presence without a single photon actually ever interacting with it.
And this is where the physics gets really wild. We aren't just talking about continuous, steady waves of light anymore. By passing a laser through a nonlinear crystal, like a KDP crystal, we trigger what's called spontaneous parametric down conversion. This literally splits a single high-energy photon into two lower-energy, completely entangled photons. We can then send these individual correlated particles of light through the interferometer to test the very boundaries of reality and information itself.
Which brings us to our final section, Part 5, Building Future Quantum Computers, the Next Revolution.
So what does this all mean for the future? Well, researchers are actively developing linear optical quantum computation, or LOQC. This is the absolute next frontier of silicon photonics. In this paradigm, we aren't just sending those bright and dark pulses of ones and zeros anymore. The photon itself becomes a quantum bit, a qubit. By manipulating its polarization within that microinterferometer, it enters a superposition of states, and that allows the system to process massive amounts of complex information all at the exact same time.
But, to build a universal quantum computer, a simple two-path setup just isn't going to cut it. Recent research proposes vastly upgrading this architecture. By introducing multiple beam splitters and multiplying the interference paths directly on the chip, researchers can route highly entangled multi-qubit systems through a complex maze. By strategically applying phase shifts along these multiplied paths, they can perform intricate probability rotations. This executes the incredibly complex multi-qubit gate operations required to run the quantum algorithms of tomorrow.
We traced a really amazing arc today, from 19th century physics to visualizing macro wind currents, all the way down to the microscopic silicon photonic chips routing the world's data right at this very second. So I want to leave you with this final thought. If a single split beam of light fundamentally transformed how we communicate today, will these multiplied, entangled quantum beams eventually unlock the ultimate limits of human computation? It's a bright future for sure, and the Mach-Zehnder interferometer is quite literally lighting the way. Thanks for focusing in with me today on this explainer, and keep learning.